Now looking at these formulas that are used to create these polynomials, these are things that we've discussed in class. We talked about this after we watched the 3 blue, 1 brown video that was very good. And we kind of understand, I hope, at this point that each one of the terms in a Taylor polynomial determines the particular derivative that we're talking about. So for example, the nth derivative is determined only by this function, this term right here. You take n derivatives, and everything before it goes away because they all turn into constants and then they differentiate down to 0. But if you take n derivatives here, the n and the n minus 1 and the n minus 2, the power rule that happens over and over and over again, keeps on canceling out everything that shows up in the denominator, and then we're left with just the nth derivative of the function evaluated at c, times x minus c. So the x minus c is going to be raised to the 0, so we know that the nth derivative of that function is just going to equal the nth derivative of that function. So basically what we're forcing this polynomial to do, we're forcing this polynomial to match our initial function. In the examples we've seen so far, it's been the sine of x. So we're making this Taylor polynomial, or this Maclaurin polynomial, match the sine of x in this case, for as many derivatives as we want to, but only at a single point. The more derivatives we use, the more the polynomial is going to hug the original function to make a better approximation. Now, the most general form of this is the Taylor polynomial, where we can center the point of tangency at any x value, so we call that x value c. About half the time, I'd say, or maybe even more, that c value happens to be 0, and we call those down here, we call them Maclaurin polynomials. And Maclaurin polynomials are the same as Taylor polynomials, except they are just simply centered at x equals 0. You can notice that if we just change all of the c's up here to 0, every single c gets changed to a 0, then we end up exactly with this guy right here. All of the x minus c's turn into x minus 0, so we don't worry about writing minus 0, so we just have a simpler formula. And whenever we can, we probably would prefer to center our Taylor polynomials around 0, simply because it makes things cleaner. But we're going to refer to both of these throughout the rest of the course, so make sure you understand the difference between Taylor and Maclaurin polynomials. Also make sure, this is pretty important, that we never put an equal sign between the actual function and the polynomial, because the polynomial is not equal to the function. It is just an approximation, whether it's a local linear approximation or a local quadratic approximation or a local cubic approximation, whatever degree you get to, no matter how many degrees you go to, it's always going to be an approximation. Do not put an equal sign between the two. All right, so for example 3, find the Maclaurin polynomial of degree 5 for the function f of x. Well, we just dealt with f of x before. Last time we took the derivative and we called it a day because we were asked to find the tangent line, and the tangent line is the degree 1 polynomial approximation, but we want now the degree 5 approximation, so we're going to have to take the first derivative, and we're going to have to take the second derivative, and we're just going to have to keep on going. But good news, this function does not get harder when you differentiate it. It just kind of cycles around to 4 different values. So we are going to end up back to where we started at the 4th derivative, and then for the 5th derivative, we are going to see the cosine of x one last time. And then we're going to evaluate this at x equals, well, this says a Maclaurin polynomial, so that means x equals 0. So we're going to evaluate f of 0. That's going to be 0. We're going to evaluate f prime of 0. That's 1. F double prime of 0 is 0. Third derivative equals negative 1. The 4th derivative at 0 equals 0. And the 5th derivative at 0 equals 1. Now these are going to be the coefficients that we see right here. That's going to be the f of 0, f prime of 0, f double prime of 0, etc. All of those are our 0, 1, 0, negative 1, 0, 1. All right, so when we find p sub 5 is going to be equal to f of 0, which is 0, plus f prime of 0, which is 1, times x, plus f double prime of 0, which is 0, divided by 2 factorial, times x squared. And now f triple prime of 0 is the numerator, and 3 factorials on the bottom, and we're going to have times x to the third. And then plus, well, the next one is 0, so we have 0 over 4 factorial times x to the fourth. And lastly, we've got this last coefficient of 1, and that's going to be divided by 5 factorial times x to the fifth. Remember that those factorials show up because of the power rule required to take multiple derivatives. So the nice thing about this polynomial is it matches the first 5 derivatives of the sine of x at x equals 0. So this should be a pretty good approximation for the sine of x. We can clean this up a bit. We'll go ahead and say that the sine of x is not equal to, but is approximately equal to 0 plus 1x plus 0x squared minus 1 over 3 factorial times x cubed plus 0x to the fourth plus 1 over 5 factorial times x to the fifth. So this is familiar to what we saw in example 2. We stopped before we got to the 7th term, but we've got at least the degree 5 Taylor polynomial approximation. All right, so now it says to use this value to use this polynomial to approximate sine of 0.1. This is pretty much the same thing we did with the tangent line, isn't it? Except it's a little bit more involved because we've got more terms. But we're just going to replace each of our x values with a 0.1. And we can say that the sine of 0.1 is approximately equal to this thing right here. Now, I'm not interested in you calculating what that is by hand. So if you don't have a calculator, then you would just leave it like this. One thing you might notice here is that as we continue on with this pattern, you're going to notice this is an alternating series. We've got a positive first term, a negative second term, a positive third term. You can imagine that we're going to get a negative next term and then a positive term after that and then a negative term, and it will continue on with this pattern forever. So if we wanted to talk about whether this thing converges or not, we could ask the question, does the sine of x, which is approximately equal to, I'm just going to stop at the third term, and we've got x not raised to the n because we've got 1, 3, 5, so I guess we can do 2n minus 1. So when n equals 1, we get 1. When n equals 2, we get 3. When n equals 3, we get 5. So that's going to give us the x to the 1, x to the 3, and x to the 5. And whatever our exponent is, that's the denominator factorial. So 1 over 1 factorial, 3 over 3 factorial, 5 over 5 factorial. 2n minus 1 is the exponent, 2n minus 1 factorial is the denominator. The only other thing we need is that alternating piece, the changing of the sign. So negative 1 multiplied some number of times. We're going to say n, but that's going to start with a negative term if n equals 1, and we want to make sure we start with a positive term, so we're going to say n minus 1. So this is the same. This is the same degree 5 polynomial that we have written up here, just in summation notation. And when you write it like that, you should realize that, yeah, the exponential function grows quickly, but not as quickly as the factorial function. So if you went through the process of the alternating series test, you'll find that this thing converges by the AST. That's something that you should know how to do. I'm not going to go through the steps now for the sake of time, but you can go back to your old notes and take a look at those, and you can see that this thing does converge by the alternating series test. Because it converges, we can talk about the comparison to the approximation and the actual value, right? Because we know that the alternating series theorem tells us that the error is always smaller than the next unused term. Well, the next unused term in this case is this one right here. So we know that our approximation, which I'm going to call p sub 5 of 0.1, we know that that is a good approximation of the sine of 0.1. And now the question is, how good an approximation? So we know that if we subtract the error, which is x to the 7th over 7 factorial, but for that particular x value of 0.1. So 0.1 to the 7 over 7 factorial. If we subtract that from our approximation, we have a good lower bound for our estimate. And if we add that same error, 0.1 raised to the 7th over 7 factorial, then we have a good upper bound for the error. So this thing is as big as we can get, this thing is as small as we can get, and what do we put in the middle? The thing that we're approximating. So not P5 of 0.1, but this thing that we're trying to approximate, which is sine of 0.1. So you can verify that, in fact, these numbers work out by punching them into a calculator. I'm, again, not going to do that because I want to preserve my disk space and my ailing voice right now. But that is a good example of how we can determine the accuracy of a Taylor polynomial's approximation of a value.